Welcome to our next video. This will be over section 8.2, where we're going to start to talk about infinite series. We've talked about sequences, where a sequence was just a list of numbers, or in terms of its plot, just a bunch of dots as we move down the axis. So I can think of a sequence where n is my input and my ANs are here. A sequence is just a list of dots. Now, a series is the sum of these. So we can think of a series as being formed by taking these sticks of height A1, A2, A3, A4, and so on, taking those sticks and stacking them one on top of the other and getting a really long stick. If the length of that stick is finite, then we say that the series converges. But if that stick continues to grow without bound, then we say that the series diverges. Determining whether a series converges or diverges is a lot trickier than determining whether a sequence converges or diverges. To check if a sequence converged or diverged, all we had to do was see if it had a limit. But since this is a sum, we've got to do a little bit more than that. And one of the first things that we can do for some easier versions of series is to examine the partial sums. The partial sums of a series is what it says, the sum of the first so many terms. So if I think of the first partial sum, it's just the sum of the first term. The second partial sum is the sum of the first two terms. The third partial sum is the sum of the first three terms, and so on. So that the nth partial sum, Sn, is the sum of the first n terms. These s's themselves make a sequence called the sequence of partial sums. And one of our theorems that we'll deal with here is that a series is going to converge with a sum of s if the sequence of partial sums, formed like I did above, converges to s. Now that's cool because that's a sequence. All we need to do is, if we can find a general formula for the sequence of partial sums, get us a general term for it. If it has a limit, then that's the sum of the partial sums, which will be the sum of the series. That's trickier than it sounds like, but we'll do a few easier examples. If this sequence of partial sums has no finite sum, then we say that it diverges. And then the series will also diverge. Here's a couple of examples where I'm going to look at their partial sums and show that these things converge. So the first one, I'm adding 9/10ths with 9/100ths with 9/1000ths and so forth. Or if you think about it in decimal form, I'm adding 0.9 with 0.09 with 0.009 and so forth. Right? This is another way of writing 0.9 repeating. I'm going to show you that this has a finite sum, that 0.9 repeating is actually equal to 1. So let's look at the partial sums. The first partial sum is just the first term. The second partial sum is the first term plus the second term, or 0.9 plus 0.09 to give us 0.99. The third partial sum is 9/10ths plus 9/100ths plus 9/1000ths, or 0.9 plus 0.09 plus 0.009, which is 0.999. I want to see if I can find a pattern here. And the pattern that I'm noticing, or that I hope that you'll help me notice, is that this is the same as 1 minus 1/10. This is the same as 1 minus 1 over 100, which is 1 minus 1 over 10 squared. And this one is going to be 1 minus 1 over 1,000, or 1 minus 1 over 10 cubed. So if I did the few more terms, pretend that I've done n of these, then I'm going to eventually have 9/10 plus 9/100, blah, 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 till I get to the nth one, right? The third one had 10 cubed here, so the nth one is going to have 9 over 10 to the n. That should add up, according to this pattern, 1 minus 1 over 10 to the n. So that's my general term. So I have that my SNs look like 1 minus 1 over 10 to the n. Now take the limit as n goes to infinity of 1 minus 1 over 10 to the n. Well, the only term that grows is the 10. That gets bigger and bigger and bigger in that fraction. Then I divide that into 1. So that term goes to 0. Which means this limit is going to be 1. So my conclusion is the series, 0.9 repeating, I'll write the series in our series form. The sum from n is equal to 1 to infinity of 9 over 10 to the n converges to 1 since the sequence of partial sums converged to 1. Just fit that one in there. All right, so let's do it again. Not always can we get a good little sequence of partial sums, but in our next example, we can get a sequence of partial sums. Let's kind of take a look at it. This, if I left it in this form and wrote out the sequence of partial sums, you might notice that I bounce back and forth, sometimes using a subscript of n, sometimes using a subscript of k. It's a dummy variable, it doesn't really matter, but I tend to fall into n's and k's every now and then. So let's see. S1 is the sum of the first term, so I'm replacing k with 1, and I get 1 over 1 times 2. S2 is the sum of the first two terms, so I'm going to have 1 over 1 times 2 plus, now the next term, will be 1 over 2 times 3. The next one, S3, is the sum of the first three terms. So the first term plus the second term plus the third term. So it's a half plus a sixth, a half plus a sixth plus a 12th, and so on. In this form, it's kind of hard to see a general pattern, at least I don't see it. And the trick here is to do the partial fraction decomposition of this fraction. Convince yourself that this partial fraction decomposition gives that this series is equal to the sum 1 over k minus 1 over k plus 1. All right, if you get a common denominator, multiply this by k plus 1 over k plus 1, this by k over k. The k's would subtract out, and I would just have a 1 over that common denominator. If I expand the partial sums in terms of this equivalent expression for that one, I can write S1 as 1 over 1 minus 1 over 2. And then S2, so I'm looking here, is the first term, 1 over 1 minus 1 over 2, that's S1. Now I have to add to it the second term, 1 over 2 minus 1 over 3. Go up here now and add up the first three terms. So take the first two terms from above. Oops, I want that to be a minus. Minus, come back here. Minus 1 over 2 plus 1/2 minus 1 over 3. The next term will look like 1 over 3 minus 1 over 4. Maybe we'll do, oh, well, let's just kind of notice what's going on here. Let's write out what Sn is going to look like. That Sn will look like 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. And then we get out to the nth term, would have 1 over n minus 1 over n plus 1. This is a sum of n terms. The parentheses themselves I put in there just so you can see what the different terms were. Take the parentheses off, and what do you notice happening in this partial sum? Do you see that negative 1/2 adds to the 1/2? The negative 1/3 adds to the 1/3. There's going to be a positive 1/4 here. And in fact, there's going to be a negative 1 over n here. This is an example of a sum that telescopes. Picture a telescope in its fully extended length, and you can kind of push the ends together and it collapses together. And here the stuff in the middle adds together to give us zeros in the middle, so it collapses and gives us just the two terms on the end. The 1 in the front minus 1 over n plus 1. So I now have a closed form for the nth partial sum. This will converge if it has a limit, and by golly it does. It converges to 1. So my conclusion is the same as before. The partial sums converge, so the series will converge. The partial sums converge to 1, the series, the infinite series that we started with, way up here, adds to 1. We're not always going to be able to show things converge by looking at their partial sums. They have to be kind of special cases. They have to telescope for us or fall into another category that we're going to cover here at the end of this discussion. So we're going to need lots of other tests beyond this. But this is the first concept of what it means to converge. A series converges if its sequence of partial sums converge. Now, an example of a sequence of partial sums that does not converge is just adding a bunch of 1s and negative 1s together. If I add the first partial sum is 1, S1 is 1, S2 is 1 plus negative 1, which is 0, S3 is 1 plus negative 1 plus 1, which is 1. The fourth partial sum, 1 plus negative 1 plus 1 plus negative 1 is 0. So these values oscillate between 0 and 1. So that clearly won't have a limit. If the sequence of partial sums doesn't converge, then the series does not converge. When a series does not converge, we say that it diverges. Diverges typically means the sum is infinite, but this one means that there's not a fixed number sum. It bounces back and forth between 0 and 1. A couple of important properties. The first one says that the sum of two convergent series forms a series that itself is convergent. In fact, any scalar multiple of those series will converge. For example, up above, we had this series, 1 over k times k plus 1, and this series, adding a bunch of 9/10ths together. I can make a new series out of that. Let me do that in blue. The series, adding a bunch of 9/10ths together, so 0.9 to the k. Now the series 1 over k times k plus 1. If I add those together and make a new series, convergent plus convergent is convergent. I knew what this one converged to. This sum converged to 1. So did the other one. So this sum converges, and it converges to 1 plus 1. On the other hand, if you have one series that converges and one that diverges, then the series formed by adding the two together automatically diverges. That goes along with the old saying that one bad apple spoils the whole bunch. So for example, if I take my series with 0.9 to the k, and I add it with the series -1 to the k, and make a series out of it, that series is divergent. Sometimes those are helpful. You'll see, though, that they show up again when we make power series later on in Chapter 8, that we can add convergent series together to get another convergent series. The other type of infinite series that we can easily test to see if it converges is something called a geometric series. And in a geometric series, we start with a number, and then the following terms are just a constant multiple added of that number added to the previous terms. So I wrote that as a plus ar squared plus ar cubed, and so on. An example of a geometric series is like 1 plus a half plus 1/4 plus 1/8. See, I'm getting the next term that I'm adding by multiplying the previous term by a half. So in this example, a is the first term, and r is the multiplier. So I can write this series as the sum from k is equal to 1 to infinity of a times r to the k minus 1 power. I told you I bounce back and forth between n's and k's. Or another quick way to write this, since 1 to any power is 1 and multiplying by 1 is 1, I can write this as the sum from k is equal to 1 to infinity of 1 over 2 to the k minus 1. Another example of a geometric series is, I'll go back down, 5, 10, 20, 40. So my first term is 5, and my multiplier is 2. I'm doubling the terms as I move down. 2 times 5 is 10. 2 times 10 is 20. 2 times 20 is 40. Now you can kind of see that these are going to grow pretty big. So this sum has no chance in heck of adding up to a finite number. That's like each day throwing money into a pile. The first day you throw $5 in there. The next day you throw 10. The next day you throw 20. And then 40, and so forth. That pile is going to grow infinitely large if you do that forever and ever and ever. Plus, you'll be pretty rich. So this second example clearly has no finite sum. The first example does. The first example is the example I always use, that if I'm standing on top of a 2-foot-long desk and I start walking across that desk, and my first step is 1/2 the entire length of the desk, so 1 foot long. Then my next step is half that length. And then from there, I take a step half that length, so 1/4 of the way there, and I keep taking steps of smaller and smaller size. I will never fall off that 2 foot long desk. This first sum is a convergent geometric series, and we're going to show that it adds to 2. To determine whether or not a geometric series converges and how it converges, I'm going to show you some hocus pocus here. Let's start with our geometric series, a plus ar plus ar squared plus ar cubed plus ar to the 4th, and so on. Goes on and on and on forever. Let's just stop it at the nth term. So let's call this the nth partial sum. So the first term is here, second, third, fourth. So the nth term should have 1 power less on the r than whatever the subscript is. Come back here. Sorry about that. There it is. Okay, so here's where the hocus pocus comes in. I'm going to take that line that I've written there, and I'm going to multiply every term by r. So I'm going to have a new line called r times Sn. So if I multiply every term by r, my first term will be ar, my next term will be ar squared, and I'm kind of lining them up here on purpose. My last term will be ar to the n, but there'll be a term right in front of it, ar to the n minus 1. Now I'm just going to subtract. I'm going to subtract the top line minus the bottom line. And when I do that, when I subtract, let me put the minus sign in here and show you. That minus sign is going to distribute here, 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 all the way down to the end. And so when I add these together, these in the middle will all add out, much like in the telescoping series. And all we're going to have left is the first term minus the last term. Now I'm going to factor out the common factor of Sn. And I'm going to have a 1 minus r here. Over here I'm going to factor out the common factor of a. And I'm going to solve for Sn. Remember, Sn was our notation for the nth term, or the nth partial sum. So now my question is, what must r look like in order for this sequence Sn to converge? Well, when Sn converges if this thing has a limit as n goes to infinity. So that's why I'm only looking at the r, because there's only one term in here that has the n, right here. R is the multiplier. Go back and look at this example. R was a half. And so if you multiply higher and higher powers of a half together, eventually you're going to be adding 0, a half, a fourth, an eighth, 1/16. That value, r to the n, 1/2 to the n, is going to go to 0. But 5, our multiplier here, number 2, is 2. That's going to keep growing and growing and growing. So does it make sense that you need this multiplier to be smaller than 1? Now, it can also be negative. So I'm going to say that this thing has a limit provided that r in absolute value is strictly smaller than 1. Notice that r can't equal 1 because then I'm dividing by 0, which means any value of r between -1 and 1 has the property that this will go to 0. If r is outside that range, that's going to go to an infinitely large number. And not only does that go to 0, it leaves me with a formula for the sum. So our conclusion is this: a geometric series that looks like this, AR to the n minus 1, converges only if that multiplier r in absolute value is smaller than 1. And furthermore, it has sum equal to a divided by 1 minus r. Massively important that you be able to recognize geometric series, because it's one of the very few whose sum we'll be able to find. Now you've got to be careful. Go back up to this example up here. A is 1, r is a half. It's smaller than 1, so it converges to a over 1 minus r. A is 1, r is a half. So like I said, if I walked across that 2-foot wide desk, I'd never fall off. I'd make it exactly to the end. Don't try to use the formula here. So if it's outside that range, that sum formula doesn't work. Got it? I think we got time for an example or two. You have to kind of train yourself to recognize these geometric series. So sometimes you've got to write out the first so many terms. Suppose we had something that looked like 2 to the k over 3 to the k plus 1. And I'm going to start my counter at 0 this time. In order to recognize that this is a geometric series, what I'd like you to try to do is write out the first so many terms. So starting with k is equal to 0, I would have 2 to the 0 over 3 to the 1, or 1/3. Now if k is 1, I have 2 to the 1 over 3 squared, which is 2/9. Next term, k is 2, I have 2 squared over 3 cubed, which is 4 over 27. Oops, I don't want to put that up there. Let me take that off. What the heck, one more term. The next term is 2 cubed over 3 to the 4th, which is 8 over 81. So you got to recognize that it's geometric, in that to get from one term to the other, it's probably easiest to notice it up here, that I am multiplying my first term, which is going to be 1/3. That's a, that's always easy to find. But I'm multiplying it by 2 over 3 each time. 1/3 times 2/3 gives us 2/9. 2/9 times 2/3 gives us 4/27, and so on. So I have the right form of a geometric series. My r, why does it keep doing that? I start talking with my hands and I hit my screen. All right, but r is 2/3. Since r is smaller than 1, this series converges to a over 1 minus r. A is 1/3. R is 2/3, so I have 1/3 over 1/3. This converges to 1. Let's look at this one. Pi over 2 plus pi squared over 4 plus pi cubed over 8 plus, and so on, is also a geometric series. Because I made it one. And I am taking each term and multiplying them by pi over 2. Pi over 2 times pi over 2 gives me the pi squared over 4, times another pi over 2 gives you pi cubed over 8, and so on. Pi over 2 is 3.14 divided by 2, so that's bigger than 1. This series diverges. So what I'd like you to do is read through the notes and look at the practice or the example problems that I have posted in my notes, and then see if you can try the exercises in section 8.2. Let me know how it goes.